Okay, to kind of review where we're at, obviously we magically have some circuits here. We've been talking about current mirrors. And the first one we looked at was the simple 2-transistor current mirror, and we saw that the 741 op-amp had several of these, not several, but had a couple of these for biasing purposes. And remember here that we had two equations here, that we had that Iref was equal to V plus minus VBE on minus V minus divided by R, and then the I out was equal to Iref divided by 1 plus 2 over beta. And then the 3-transistor current mirror, which we have over here, we saw when we analyzed this the other day, we got that Iref, and remember the path here that we chose for Iref was, here I'll draw it here, was that we went down this way for the path. So Iref, the equation we ended up getting, was that this was equal to V plus minus 2 VBE on minus V minus over R. And then that we got I out being equal to Iref over 1 plus 2 over beta times beta plus 1. And in both of these cases here, I'll just write it up here. We had that my output resistance for these was the same, which was basically this little RO, which was due to my early voltage. So it was VA over I out was what the output resistance was. Now, remember what we said here. The nice thing about the 3-transistor current mirror is that it has less dependence on beta, and we illustrated that by looking at an example of maybe beta being 20 versus in this case you'd have 1.1 that you're dividing by, and in this case it was, I don't even remember, but it was because we ended up having 20 times 21, so which was 400 and 20, and so we had a much smaller number, and so we got that I out was approximately equal to Iref in both cases, but for this case here we were more beta independent, and that's actually an advantage for us because not only does it matter, it's like, okay, well, when we have different betas, we're beta independent, but it actually matters because over the life of a transistor, beta is going to change, and it tends to get smaller. So you might manufacture a transistor that has a beta of 100, but over its lifespan being used, the beta might go down to 50 before the device is no longer being used. And so it's much nicer if we're really concerned about the biasing currents, this 3-transistor current mirror will give that for us. Now, there are other types of current mirrors out there as well. They are in your textbook, and you can also find these, lots of websites have it. There's a 4-transistor current mirror. There's something that's called a Wilson current source, and then there's something that's called a Widler current source. They all are kind of based off of this original 2-transistor current mirror with some small variations, and of course the variations are going to either vary what the output current is versus Iref. Most of these still though all have the same output resistance. Okay, so let's move on here to what we want to look at here next. Next we're basically going to look at the same thing, except we're going to look at current sources with Mosfets. Now, the key thing we have to remember that's different about bipolars and MOSFETs, remember bipolars are current controlled, so we're looking at all the currents, but MOSFETs are voltage controlled. So we need to make sure to be careful with that. Okay, so let's look at our first one here. So the first way we're going to draw this here, so we'll just draw a current source here calling this Iref. We'll talk about how we can get that current. And then we've got our MOSFET. And we'll just do an N-channel MOSFET. V plus up here. And my gate. V minus. And then we'll call this still M1 and M2, and this is ID2, which is the I out that we're looking for. And one last thing here, of course, just like we did before, we're going to tie the gate and drain together on the one transistor. Now, if we look at this, I mean, we shouldn't be too surprised by this. It looks like the exact same kind of current mirror that we had for bipolar transistors. But the analysis is, of course, going to be different because of the fact that we are dealing with MOSFETs as opposed to bipolar transistors. So let's look at the analysis here. So, well, first off, let's look at some things here. First off, I'm going to go ahead and just erase this M1 and M2. We're going to keep that in mind here. I'll just write it off to the side here, M1, M2. Okay, so we have a voltage here, and this is VDS1. But if I think about this just for a second, just like with a bipolar device, because we're shorting the drain and gate together, that's going to be the same thing as VGS1. Now, the other thing we should look at here is that this is a gate voltage, I'll say VG, and obviously the two transistors are tied together, and just like we did with bipolars, we're going to assume the transistors are matched, and so that voltage is the same. So we have here a plus minus VGS2, and then we do have a plus minus VDS2, but we can quickly see here from this that VGS1 is equal to VGS2, which I'll just call that then VGS. Just like we had in the bipolars, you know, we had that VBE being the same. Well, we shouldn't be shocked. We get the same thing with the MOSFETs. Okay, well now we have to look at the actual equations for the current in order to get this here. So let's look at what we have here. So remember, for a MOSFET, the current is equal to Kn. I don't know why I put a capital N, we usually use lowercase. VGS minus the turn-on voltage squared. Now again, we're going to look at the two different devices here. So what do we have here? Well, VGS2 is equal to VGS1. So we have here that ID2 is just going to simply be, and I'll emphasize here, Kn2 times VGS minus VTN2 squared. Now this is of course assuming it's in saturation mode, which, you know, that would make sense. But now what we need to do is we need to figure out what is this. Well, we know that ID1 is equal to Iref. I mean, that's just right there. And how do I know it's equal to Iref? Because you might say, well, wait a minute. If I look back at the diagram here, this is Iref, and then this would be ID, and then there's some current here that I'll just call I. But I claim we should all know what this current is. This current is simply equal to 0. How do we know that? Well, remember, for a MOSFET device, we know that the current going into the gate is 0. Now, modern MOSFET devices, that assumption isn't actually 100% correct. There's something that's called gate leakage, but we're looking on what would be considered a macroscopic level, in the sense that we're looking at larger scale MOSFETs and not the really tiny ones that are being used in modern, like, microprocessors. Alright, so let's go ahead here and then write an equation for ref here. So we have then that Iref is equal to Kn1 VGS minus VTN squared. But this VGS, this is the same VGS, because again, remember, VGS here between these two MOSFETs is the same. VGS1 is equal to VGS2, which is equal to VGS. Okay, so that's the same. So what I'm going to do here is I'm going to solve for VGS here in this equation. And so if I solve that here, I'm not going to show all the steps, it's just simple algebra. Iref over Kn, square root of that, plus, I should emphasize this is VTN1, VTN2 is equal to VGS. And so then what do we get here? We get that ID2, which is I out, is equal to Kn2 times the square root of Iref over Kn1 plus VTN1 minus VTN2 quantity squared. Now, what's the assumption that we made with bipolars? We assumed that bipolars were matched. We're going to make the same assumption here. We're going to assume that the transistors are matched. And then something really cool happens with the MOSFETs here, because what do we have here? Then we have that VTN1 is equal to VTN2, and Kn1 is equal to Kn2. And what do we get here? Well, sorry, I just lost myself. We have these two things are going to cancel each other out. So we're going to be left with I out equaling Kn2 times the square root of Iref over Kn1 quantity squared. Oh, but wait a minute. We got a square root that we're squaring, so I just get rid of it, and we're assuming kn2 is equal to kn1, so we cancel those out, and we wind up with I out is equal to I ref. So in this case, we actually get for the Mosfets that this I ref is actually just equal to I out. So we actually get a nice current mirror application here. But that's again assuming the transistors are matched. Now there is one other thing though that we can keep in mind here, and it's that Kn, remember, was equal to mu n Cox over 2 times W over L. So when you're manufacturing MOSFETs, you can manufacture them to have the same mu n and Cox, but I'll just say have different W over L relationships. And L is going to typically be the same for the devices so that we can get, well, I shouldn't say that, they do vary the length, but the W over L, we can have different W over L relationships, which what that gives me here is we can actually manufacture transistors so that I out is equal to W over L for the second MOSFET divided by W over L for the first MOSFET times I ref. And just to emphasize, these W over L's are called aspect ratios. So that's something that's kind of cool. So you can actually set it up, like for instance, you could set up a current mirror so that based off the reference current, you get half the current for biasing, or you could get twice the current for biasing. So that's kind of an interesting thing you can do with MOSFETs.